Definite integrals. At this point, you might have some feel for what an integral might be. Some feeling for a bunch of stuff added together, but we're really going to break it down into very specific terms here and do some examples of some actual definite integrals here. To do that, we need some notation that you haven't seen unless you took data management. And I don't need a lot of it, but I do need to introduce it a little bit. It's not that complicated, but it's very helpful, the notation that I'm going to give you here. Writing out these required sums. See, I hope while we were writing out these sums, things like 1/2 times 2 times 11/5 cubed, plus 1/5, 2 times 12/5 cubes, plus 1/5 times 2 times 13/5 cubes. I hope while you were writing it, in the back of your mind you were thinking, I gotta believe there's a better way. You know, there's no way this is the math of building iPhones and sending space shuttles to the moon. Like, there's no way this is what's going on in the back rooms of these massive calculations. And you're exactly right. This is the core idea of what we're trying to accomplish. And then we're going to use specialized notation to shorten this down. So things get more complicated to understand what's happening, but easier to write as we go. The exact same as the derivative, right? 2 to 2.1, 2 to 2.1, x plus h cubed, expanding all those x plus h's. And then as we got better at it, we were able to shorten down the amount of work you had to do. To express a sum in compact form, we use sigma notation, it's called. In mathematics, the Greek letter sigma, there it is. Looks like one of our sideways, sort of like an E for us, you know, sideways, but with a little angle in between, sigma. Great Greek letter. Stands for sum. And this is actually the capital sigma. Those of you in data management might have ran into little sigma for standard deviation. But this is capital sigma. Sigma sum, you know, sum. Consider the following expression. Jumping right in to show you exactly what sigma notation can do. And hopefully, by the end of this one, you're like, oh, that's going to make writing this way easier. You know, right off top. So this says k equals 1 to 10. There's a lot going on here. What this is telling you to do is it's saying, do the sum. So as soon as you see the sigma symbol, you're thinking, okay, do a sum. Add up a bunch of stuff. What are we adding up? You're adding up k values. What are the k values? Well, they go from 1 up to 10. That's simple. So you do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Not a fun sum to write out all by itself. Not even compared to some of the ones we've been doing. So that's not a fun sum to write out all by itself. But this sigma notation ties it up completely. It just says add up. What am I adding up? K values. Start with 1, end up at 10. Okay. And of course, we get the sum of 55. But in this particular case, I actually don't really care about the 55 all that much. You know, like it's like the answer's over here. I don't really care about the answer here. It's more about the notation and understanding the power of the notation. There would be a simple way to write those sums that you see on the board just in one little expression like this. 1 to 10 of blank. You know? Easy peasy. In general, if they give you sigma notation, you start with k as 1, and you go all the way up to the highest value, whatever they give the highest value, and you just sub the number into each one. You go take the 1 and sub it in to the expression, just like you would for a function or for anything else. Sub it in, then sub 2 in, then sub 3, and you're like, is it always 1, 2, 3, 4, 5, 6, 7? And the answer is a big time yes. We always go 1, 2, 3, 4, 5, 6, 7. Like, what if I don't want 1, 2, 3, 4, 5, 6, 7? You'll handle that in the function. You'll go, oh, no, I don't want 1, 2, 3, 4, 5, 6, 7. So I'll multiply everything by 2, and then I'll get 2, 4, 6, 8, 10. So you can get whatever you want, actually. You're not really restricted by the 1 to 10. The 1 to 10 is just the term numbers. You know, so you'll see, just like f at 1, f at 2, f at 3 doesn't restrict you to what values you can get at all. It's just numbering the values that you get. Here's some more examples. Oh, separate page. Okay, so k equals 1 to 8 of k squared. So I'm going to need a little space to do that with you. That should do it. Oh, there they are. Very good. So I'll do each of these examples to give you a little more experience with this sigma notation. So the first one says k equals 1 to 8. All that really tells me is I'm going to have 8 terms to add up here. And I start by subbing them each in. So I want a nice, what's coming up? Easter? I'll use a little Easter purple here. So I take the 1 and I sub it in, and I get 1 squared. That's the first term, 1 squared. Then I add to that, I take 2, the next highest k value, 1, 2, 3, 4, 5, 6. I sub 2 in, and I get 2 squared. And then I get 3 squared. And then I get 4 squared. 5 squared. How do I know when to stop here? What's the last k value I sub in? 8. So it tells you. These are called the limits of summation. They say from here up to here, just keep subbing and adding, subbing and adding. And the reason this was invented was because of questions like the ones you see on the board like this. We don't have to write all this out. We want a nice compact notation where we just tell people what you're going to be subbing in all the way along here. And in fact, you can probably see by this, you can really see, the same sort of feel. It's just cubes, that's all, and square. You can set this all up very easily. Oh, and then it wants the actual sum here. So, so actually calculate this up. 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64. Ooh, there's a fun sum for my head. 113, 149, 174, 190, 199, 204. Do I trust my brain on a Wednesday? Oh, I wish I did trust it. Wish I could just go with it. I'm going to try it. Okay, exit out of this. 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64, 204. Still got it. I can still do simple addition. Look at that. Okay. Another one. K equals 1 to 4. So this time only 4 terms. And it's k equals 1 to 4 of 1/4 times 3 to the x. Now, note that k equals 1 to 4 of 1/4 3 to the k. I can pull the 1/4 out. It's just a common factor. It was what I was doing on the board before. It's just common factoring out. If you've got a number in there that doesn't have any k's in it, it can just be common factored out. I'm not going to do it. I'm going to show it to you at the end. I'm going to write it all out like it's, you don't have to, but it can sure make your life easier. So my first term is 1/4, 3 to the, what's the first k value? 1, so I put that in there. Then 1/4, 3 this time, 2. Then 1/4, 3 cubed, and 1/4, 3 to the power 4. There's only 4 of them this time to do. Do you see how the 1/4's in all of them, though? So it would have been easier if at the start I had kept that 1/4 out front, and what I would have ended up with is 3 to the 1, 3 to the 2, 3 to the 3, and 3 to the 4. That's all that little sidebar is saying is if there's some clever common factoring you can do, you can save yourself a lot of writing. Even though sigma notation saves you a lot of writing as it is, you can save yourself even more. And so then I get 3 plus 9 plus 27 plus 81. So I get 108, 170. I think it's 120 over 4 is 30. Now, it's Wednesday, so I'm not going to believe in Mr. Todd's brain too much here. So I just want to go 3 plus 9 plus 27 plus 81 in my calculator. I get 120, and when I divide 120 by 4, I get 30, adding all that stuff up. Any questions about summation notation? Very handy stuff. Huge applications. It can get more complicated than this. You can come up with formulas for different sums and so on. There's lots more to know about this. But this will be enough for what we're doing. To know we're adding up some stuff and we're adding it all together, which is exactly what our sums have been doing. More time here? Oh, back to here. 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 I did those, yes? Notes. The numbers below and above the sigma are called the lower limit of summation and the upper limit of summation, respectively. Okay? The values from the lower limit of summation through the upper limit of summation are integers. So we always go 1, 2, 3, 4, 5. I'm sort of lying. You've got other choices. You could go 7 to 20. You go negative 20 up to 18. But it's always integers. You're always going up by 1 every single time. It's up to you to put what you need in the expression here. And it's actually not a problem. You're like, well, what about this? What, can I do this? It's not really a problem once you get used to it. It's the number you go up to. In these two cases, it was also the number of terms. See, 1 to 8 was the last thing you're going to sub in, but it's also the 8th term because I started at 1. But if we didn't start at 1, it might not be the number of terms. You're right. Other questions? Okay, here we go, Riemann Sums. I mentioned the name of it, and we've even used a program on your calculator called Riemann Sums, but here's what a Riemann sum is, and it's not we've really been doing them already, so I'm redefining something that we've already been doing. So there he is, Friedrich Bernhard Riemann. The sums in which we are interested, such as LRAM, MRAM, and RM, are all called Riemann sums. So everything we've been doing, they're all called Riemann sums. And there's more types of Riemann sums than those, but those are 3 of the types. Riemann sums are constructed in a specific way as follows. Now, if you had concerns about positive and negative stuff, and LRAM, MRAM, RM, some of that gets explained here. This is like, let's just go a little deeper with all of this and make sure it's clear. And then it goes the opposite way. It goes really simple by the end, okay? Begin with a continuous function. To do Riemann sums, we start with a continuous function. If it's got breaks and so on, then maybe we have to change the rules. You're like, well, what do you mean change the rules? You'll see. I do a couple of non-continuous ones at the end and say, well, here's how we're going to handle it if it's not continuous. We need to know what kind of continuity problem we have. For now, let's just say, to talk about it, let's just assume it's continuous, and then we'll deal with non-continuous functions when we get to them. Notice we got negative values in here too. So if the examples are all like, this is all fine, but what if it goes negative? Don't we have negative area then? Yeah, we're going to talk about that now. We just stuck to positive ones to start off with. So by choosing n minus 1 points between A and B, and that just meant divide this up to some number of sub-intervals, and why it says n minus 1 is we're giving some latitude here. Not 5, not 10, not 20, not 1,000, any number of intervals you want here. So we'll call those points, we'll give them names. x1, x2, x3. Those are the numbers I wrote across the bottom there. 10 fifths, 11 fifths, 12 fifths, 13 fifths. They each have a number, x1, x2, x3, and so on. And they all have to be between A and B. Why would we select numbers outside of A and B? We wouldn't. We'd select numbers between A and B. Notes. The points x1 up to xn minus 1 don't need to be evenly spaced. When we did it, because it's easier, we always said, let's make all the rectangles evenly spaced. Technically speaking, they don't have to be evenly spaced. If there's a situation where it's more convenient to make different spacings, I'm not warming up for that, actually. That's later courses. We just mention it now. They don't have to be evenly spaced, even though we always will. We'll evenly space them. And for consistency, we denote x0 by A and xn by B. That's what I was warming up to when I said B minus A. We'll call the first x value A, and we'll call the last value B, and all the other ones will number as x values all the way through. Not a real big deal there. The set of these numbers is called the partition of AB. That is, this list, 11 fifths, 12 fifths, 13 fifths, or whatever list you have, it's called the partition. I don't know if I use that word again in this course. But I just mentioned these words. I just throw them out there for you. Looking more closely at the n subintervals, we see the kth subinterval has length delta k equals xk minus 1. What? We've got these intervals out there, and maybe you get to an interval, and let's just, to really understand what they're getting at there, let's just imagine that I haven't broke the intervals up evenly. And you look along, and I've made crazy intervals all the way along, and somewhere along the way, you get an interval here to here, and I'll put numbers on it. You're looking at my list of numbers, and here I used 7.2, and here I used 7.6 as two different values. It wasn't 0.4 all the way along, but this particular one was 0.4. And that's all they're saying there, is if you want to find the length of a particular interval, just take the upper minus the lower, and you'll find out the length of that particular interval. This is a great move in math. When expressions come out like this, I used to struggle with these so much, I couldn't follow what they were saying. And then I stopped trying to follow what they were saying and just go, well, what if these were two numbers? Just let me put two numbers in. And as soon as I could see it with two numbers, I'm like, oh, you're just saying that the width of the interval is the higher minus the lower. That's just delta y or delta x, all the stuff that we've been doing in the past. So not as fancy as it's making it look here. It's making it look like something fancy is going on. It's just saying in fancy notation, if you want to find the width of an interval, take the high one and subtract the low one. You're like, oh, that's very, very nice. Thank you. Thank you for explaining that. So there's all these different subintervals we have. In each subinterval, select a number. Remember what we're trying to do. We make a subinterval, and then we choose either the left endpoint, or the right endpoint, or the middle, and those were convenient for us. But you can select any number in there, actually, to get an estimate of this rectangle. Just our purposes, left, right, and middle, were three convenient ones. Anything other than that choice becomes sort of difficult to choose. But you could choose any number if you wanted, any number in between there to get your estimate. So you got all these delta x's, and then you got all these c values that you've selected in there that you're going to use as your points. These are just the left. Maybe these are, if you use LRAM, these are just all the left endpoints. If you use RRAM, it's just all the right endpoints. Nothing too complicated here. All we're doing is giving you a little freedom. Make the rectangles as wide as you want, and choose anything in that rectangle to find your y value. You can draw the rectangle anywhere you want. Okay. Well, anywhere. Won't you get different answers? Yeah, LRAM gives a different answer than RRAM, gives it a different answer than MRAM. But all those numbers will be close, and we'll take care of that when we turn it into not 10 rectangles, not 100 rectangles, an infinite number of rectangles. And none of these details will matter anymore as soon as we do that. As soon as limits come along and go, what if we use n of infinity? Then all these details just squish right down into nothing. Just like it did in calculus. Like, how close do you have to get? 2.1, 2.01, 2.01? That's the question the advanced functions people are asking. Well, what can I use 2.005, 2.005? And you're like, yeah, use whatever you want. Just make sure you're getting closer. You'll get the answer. You know what's going to happen next. You know it doesn't matter what you select. As long as you keep getting closer, you'll go 8.9, 8.99, 8.99. You'll get to the answer. That's what I'm saying here. Any rectangles you want, make them as wide as you want. Any x value in the rectangle, you select anything. LRAM, RRAM, MRAM, 3/4 RAM, 1/4 RAM. It doesn't matter where you select in there, because it's just going to be an estimate. The choices you make might make a better estimate, but in the end it won't matter. If this seems to be going fast, it's because I'm just giving you the whole idea here. All these little details are just contributing to the idea. There's never on a test where I'm going to go, so find the kth interval by going, no, that's not what this is about. The big idea, the whole thing is, go ahead, any rectangle you want, make them as big as you want, then choose some x value in that interval to make your rectangle. On each subinterval, make a rectangle. So this is now getting to the big idea. Go to your subinterval that you've selected, choose an x value to make a rectangle so that you can estimate the area in that section. Yes, there might be better choices. Then do it again. Then do it again. Then do it again. Just come up with all these rectangles of whatever you're doing here. And then you'll have these rectangles, and they'll have numbers. It'll be the first rectangle, the second, the third, the fourth, the kth, the 11th, all these different rectangles you've got. Then for each rectangle, find this product. This looks complicated. This is the first moment I'm going to jump in and really make a big deal about something, because I want to make sure you understand that this is not complicated. This is just, Oh, I thought I clicked on the other thing there. I didn't. Pen. Okay. This is just base and height. That's all we're talking about. After all that blah, 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 all we're saying is take the base of each rectangle and multiply it by the height. They happen to put the height first here. At least what the height would be in my mind. The height in my mind is the y value. The base is the delta x, the width of the rectangle. Note this product can be positive, negative, or zero. Up till now, we've been doing all these positive areas over here, but apparently negative is allowed. Of course it's allowed. If you go underneath here, you're going to be multiplying by negative y values, and we have to deal with what the heck does that mean, and I will deal with it in the next couple of lessons. They could also be zero. We ran into that a couple of times, where it was like, oh, the actual height of the rectangle was zero, and I got zero area out of that as an estimate. Like, it wasn't actually zero area. I know. It was close to zero, though, and that's why we got zero as the estimate. The sum of these products is this. Okay. Now, this I want you to understand. All that other stuff is like just background details, big picture type stuff. This is what I want you to understand. What we are writing out is we are writing out a sum. And we had 1 up to n. Yeah, we started with the first rectangle, then the second rectangle, then the third rectangle, all the way up to n rectangles. We got to choose the n. This is just number of subintervals. And then this delta x was just the base of the rectangle. And this f at whatever was just the height of the rectangle. So what, after all that explanation, this says, add up all the base times heights. You're like, you just went 4 slides to say add up all the base times heights? Well, there's some more details there, actually. There's some pretty deep details going on there. But that's basically what we're up to here, is if we want to find the area under a curve, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or however many rectangles. We go the base times height in each one, and we add them all up. And that's what this sigma notation is trying to say. I paused for questions because I on purpose, moved through some of that pretty quick because I didn't want it to become the issue, the delta x, k's, and everything like that. That's not the issue. The issue is this perfectly describes in a simple notation what we're trying to accomplish. Add up all the base times heights. That's what it's trying to say. Do you have questions about that? More time there? I didn't write much there. But. This sum is called the Riemann sum. A Riemann sum is adding up all the rectangles. I'm lying a little bit. We could go to other shapes. There might be better choices here than rectangles. But we'll leave it as rectangles until I get to those things. I'll fix the lie later. I'll come back and say, hey, what about trapezoids? And then we'll have some other choice. Well, let's just leave it at this. Riemann sums are about adding up rectangles. Yeah, that's the whole deal right now. Some important points on this. LRAM, MRAM, and RRAM are all Riemann sums. Smaller intervals lead to better approximations. In the middle of that, I said, oh, you can use whatever width you want. You're like, wouldn't that make the estimation worse? Well, yeah. Yeah, obviously smaller intervals are better choices. The point is you can use whatever interval you want. And you can see here, when you use large rectangles, you see how much area it's off here? Now, when there's positive and negatives like this, you're like, oh, it's off negative a little bit, it's off positive a little bit. It sort of will all work out. And it sort of does work out to a good estimate. But smaller rectangles, you see how little area is off here, And you can imagine if I went to even smaller rectangles. Let's say this is 20 rectangles on the left-hand side here. And this was 50 rectangles. This estimation would be better. Then 1,000 would be better. In the math coming soon, we're just going to go, you know what? Let's just go to infinity. We'll use an infinity number of rectangles, and then we'll be perfectly accurate in all this. The longest subinterval, okay, this is just a technical detail, okay? Before I explain that, I just want to say, again, if we go and make these subintervals really, really small, we're going to get a great approximation. The smaller the intervals, the better the approximation. So this is going to put it in fancy terms. the longest subinterval. So you see, they've used all different subintervals here, all different widths here. And look at this. Look how long this one is. You know, there's one really long subinterval in there. And as I was explaining it, I hope you were thinking, yeah, but we don't really want long subintervals. That's going to be bad estimation. So we look across them and say, what's the longest one? And we call it the norm. And the norm's the one we're worried about. It's the one that's going to throw things off. As the length of the subintervals approaches 0, all Riemann sums for a given function on the interval approach the same value. Okay, what we mean by that is, let's say this half of the class did LRAM on a certain function. Yeah? And then you guys all did MRAM. And I did RRAM on a function. And we all did it with 4 subintervals. We'd find our answers were really far from each other. And we'd go, this isn't working very well. And I go, you know what? Let's do it again. Well, let's do it with 10 subintervals. And what we do notice is we look at our 3 answers and they'd get closer to each other. And then you go, okay, let's go 100 subintervals. We do all our calculations, come back and say, then our answers would be super close. Yeah, they'd just keep coming closer and closer. And the difference between LRAM, MRAM, and RRAM would start to get crushed down to a value, and we'd go, there, that's the actual area. How far will we have to go? Well, it depends on how accurate you want to be. Same as 2 to 2.1, 2 to 2.01, 2 to 2.01. You want a better answer? Get closer. Get more intervals. Yeah? And MRAM, LRAM, RRAM, any RAM, anything you do, those answers will just get squeezed in closer and closer to each other the more intervals you go to. Use less intervals, not accurate. Your norm is big, your biggest subinterval is big, you won't get accurate answers. But you just keep adding rectangles until your answer gets good. This condition is assured by requiring that, oh, this is it. This is where limits come in. You know, we did all those, the calculus, the regular calculus people are doing limits right now and they're just dying. I don't know if you remember doing limits. Like limits was like big work, big understanding, lots going on, right? The result of all that thinking is that I can say a sentence like this and you go, yeah, I know what you mean. Hopefully, after all that limit stuff. If the norm goes to 0, that is, if the largest rectangle approaches 0, like its width is like almost 0, we'll get a very, very accurate answer. You know? We can let the limits take care of the rest. A small biggest rectangle would mean that our answer will be extremely accurate. And all of these different addition methods will come close to each other. Well, here it is, the integral. After all that, we're going to call that thing the integral. Oh, lots going on here. Lots going on here. I want to really pull this apart so you know exactly what this is saying. Okay? So I'm going to add some things to it. Let f be a function defined on a closed interval a to b. Technical detail. You know, we're like, we have to have a nice function. You can't have crazy things that have asymptotes and everything like that. That's not true. I can deal with asymptotes. I'll get to it. But let's just, for now, to make the definition, we'll say it's got to be nice, a nice function. For any partition, you break it up any way you want. You start with wide subintervals, you go 1/5 every piece, you do any partition you want. But the number ck be chosen arbitrarily. So, again, there's the base, the delta x's, all the way along the way. There's the height, the y values all the way along the way. And this is just the sigma again. Add them all up. Up until that moment, you're like, you just went another slide and just said the exact same thing. Add up all the rectangles. Yeah? And then there's this thing sitting out front going, limit as the norm goes to 0. That means we're going to move that widest rectangle. We're going to move it towards 0. That's the same as saying we're going to go to an infinite number of rectangles. We're just going to make sure that thing goes closer and closer to 0. Smaller and smaller rectangles. As we go smaller and smaller rectangles, if we get an answer, and it heads towards an answer, that thing will call the integral. It'll be the number of the area. Imagine us doing this thing, LRAM, RRAM, MRAM, okay? And as a group, we're averaging our answers. And we do the area under a curve. And then we go, oh, we average, we get 7.9. Then we do it again with more intervals, 7.99. Then we do it again with more intervals, 7.9999999. You know, we just keep going. That number that we know it's heading towards, which is 8, is the integral. So as it turns out, the integral is just a number. When we're all done this, when we did these areas up here, what we came up with was, Oh, I didn't write one on the board. Another one was 140.81. The answer's a nice simple number. Not some crazy representation or a graph or anything like that. We're just looking for a number here. So let me just put that here. A number. And underneath, I'll put area question mark. It doesn't have to be an area, but it sure feels like it has to be an area because of what we've been doing. But I did a couple of volume examples to show we don't have to be talking about area here. Area is just the easiest thing to think about when we're doing all this. And this says no matter how you choose your delta x's, and no matter how you choose what x value to use in each interval, if you head this thing towards 0, so you use LRAM, you use RRAM, and I use MRAM, if we go to an infinite number of rectangles, we'll get the same answer. Yeah, those will all approach each other. Why does that happen? Well, the only reason LRAM and RRAM give different answers is because this rectangle has some width. The left-hand value is a lot different than the right-hand value. But as we go to smaller and smaller x values, those two numbers that you're using for LRAM and RRAM head towards each other, and our estimates get closer and closer. The existence of definite integrals, if the function's continuous, we'll be able to do its integral. That is, if a function is continuous on an interval AB, then we'll be able to do its integral on AB. Continuity is very helpful here. When it's not continuous, I got a couple of tricks in my bags. And then this. After all that discussion, you're like, yeah, that's fine. Mathematically, it's true that I could choose any interval. That's all good to know. But in the end, we're going to choose subintervals of equal length because that's way easier. Why would you go some other way? And we won't see why you would do that until way later. Might be the third university calculus course before you start going, ooh, maybe we should select the subintervals differently to help with the math. That's all you would do, is to help with the math if that got complicated. For us, much simpler, equal length subintervals. Here's another way of saying the same thing. Let F be continuous in AB, and let AB be partitioned any way you want. And here's that little formula there that I stole in earlier lessons, that delta x equals b minus a over n. Boy, it looks fancy, doesn't it? Delta x equals b minus a over n. It looks fancy, but all it's saying is take your highest x value, subtract your lowest x value, divide by how many intervals you want, and that'll tell you how wide to make the intervals. Yeah, not really complicated at all, but a handy formula to write down. You saw me write it down a couple times earlier to use. So the definite integral then will be, now again, look at this second part of the integral. Again, that just says add up the rectangles. Take the base and heights and add them all up. But this time it says over here, instead of the norm going to 0, it says limit as n approaches infinity. This is what I've been warming up to for a few lessons, is what we're going to do is not 5 subintervals, not 10 subintervals, an infinite number of subintervals. And it's not clear how we're going to exactly pull that off yet, but we'll get there to where we're like, we don't have to choose some number, we'll just go to infinity. Yeah. And again, arbitrarily chosen. Apparently we can choose any y value within the subinterval. So some integration notation. Oh, this is it. Like, you look at all this, you're like, even after all that, Mr. Todd, even after switching from these crazy long lists of summations that we were writing out to a nice simpler notation, this is like a perfect description of what we're doing. That's what this is. It says, go from k equals 1 to n, multiply the delta x's by the y, find each area, and add them all up, then go to, when it's all done, go to an infinite number of rectangles. That's a perfect description. And there's no way we're writing that every single time we go to do one of these. The simple, beautiful, encapsulating, perfect notation for this looks like this. It just says, little small elongated s here, and that's what it actually is, an s for summation. It says add up from a to b, f at x dx. It just says add up the area of f at x dx. This doesn't need much explanation. And the reason it doesn't need much explanation is it's like the first day you see f prime. I don't know, you maybe don't even remember. I walked up there and I wrote f prime. You're like, so I just put like a little 1 beside the f, and that means derivative? Am I supposed to understand that? And I didn't say much about it. I just kept right on going. within a couple of days, you're like f prime this, f prime that. Yeah, like f prime wasn't a problem. I'm telling you, this notation will not be a problem. You can come back and look at it in a couple of lessons and look at where it came from. I'm telling you, don't worry about what this exactly means because we're going to beat that to death. What does this mean? It means this. It means the same thing. It wraps it all up in one little bundle. It says, find this area. That's what that says. Find that area. Add up all those rectangles. Get it done. It's called Leibniz notation. You've heard of Leibniz before. He came up before with some beauty notation. dy by dx, which at the time seemed like a pain. And then later on we found out like, oh, we kind of need Leibniz notation for this question. Same here. Writing this out every time? No. This will be a nice convenient notation to write all the stuff we've been talking about. There it is. So good. The end of high school, most calculus students will be left with the derivative is everything. Calculus is the derivative. The derivative is calculus. It's so beautiful. And those of you learning about integral calculus will go, hold on a second. Let me show you something else. And this is the something else. And like the derivative, on day one, it's like, okay, well, I'm marginally impressed because you seem pretty excited about it. But every day from here on in, you're going to see something else that this thing can do. It's called the integral. It's the integral of f from value a to value b. Now, I'm going to say, again, in math we lie sometimes, and we say things are pretty simple when in fact they're going to get complicated. But for a while, it's going to be pretty simple. I'm going to give you the function. I'm going to say, just like in derivatives, here's the function, take its derivative. Yeah? And I'm going to give you from where to where. I'm going to say find its area from 5 to 11 or from 0 to 8 or whatever. You're going to have all that information. So this is like a generalized notation that we're going to have all that information. I'm going to do a couple in just a minute. This thing is called the integral sign. It's an elongated S. It's just a long S that we draw. The A and B are the A is the lower limit of integration. The B is the upper limit of integration. And then, of course, the function inside is the integrand, it's called. It's just the function. Yeah. I had to relearn that word integrand when I came back to high school because I didn't use that word all that much, integrand. But that's what the word is. And then x is the variable of integration. Remember dy by dx? That dx told you what variable are we using. That's what this is. It tells you what variable we're using. And there's a lot more to the story. Yeah? Note that integral of a to b f at x dx, integral of a to b f at t dt, and integral of a to b of f at u du are all the same. Why are they all the same? Let's just imagine that we go back to grade 9. And you're doing a question on remember the plumber questions? Yeah, the plumber always made $40 for the service call plus $20 an hour. And if you graphed it using x and y, I often discourage that. I'm like, why would you use x and y in here? But if you did x and y and you found the area under the curve, you'd get a certain answer. You didn't do that in grade 9, but just to extend it into grade 12. And if you used x and y, you get a certain answer. If instead somebody used n and c, graphed the thing, and found its area, they'd get the same answer. So these variables, this x variable, like it always has been, is just a dummy variable. We've been using x all the way along because it was convenient, but as you head off to physics, you'll probably use t. As you head off to another class, you might use u in a financial class. So the actual variable we use inside doesn't change what the graph is or what the area is underneath. Since the letter chosen for the variable of integration does not matter, it's often called a dummy variable. This freaks people out because we've done so much work with x. All I'm saying is if you label the x-axis as something different, you're not going to get some different answer because you chose a different letter. The definite integral and algebra. Okay. If f at x is non-negative. Okay, that's the kind of questions we've been doing so far. Positive numbers makes it easy to think about this as area because all the spots were positive underneath here. So it was easy to talk about the area thing. So let's just talk about that for a second, and then I'll delve into the negative part, which isn't actually a big problem. The product f at ck times delta xk, seen earlier, is the area. So this is the one. I'll put a red star beside it. If that idea, if this little expression has been confusing you, even though I've been putting a little base and heights on them, come back to this picture. It's the perfect picture to show you that we're just taking the base of this thing and multiplying by the height. That expression right there is just area of one rectangle. That's all we're saying there. And it's got some fancy symbols there, but that's all that's really happening there. K equals 1 to n of that is the approximation of the area under the curve. This is what we've been doing. Is it saying we'll approximate it by doing a certain number of rectangles. And then when we go limit as n approaches infinity, we'll get the actual area, if it's possible to get the actual area. I just nudged that in there, like derivative. Like if it's possible to get the derivative, because every once in a while a derivative didn't exist at a cusp or something like that. So I'm just getting ready for those special cases now. For now, we'll approach it like all these areas can be found, even though some areas can't be found that easily. Therefore, this is it. After all those lessons, after all those little pieces, here's what we're trying to say. If y is non-negative, you're like, wait a minute, you just said non-negative again. You mean this thing doesn't work for negatives? No, we just got to think a little bit for negatives. We just have to think a little bit. If y is non-negative, and we can do its integral over an integral ab, then the area under the curve from a to b is integral a to b of f at x dx. That's what you can go home tonight, get some spray paint out, and spray paint it on the wall of your rooms. Or get a nice big magic marker and just write right over top of the paint on your paint job on your walls. And you can defend that the rest of your life. That is perfectly good stuff to put on your wall. That's how powerful that is. He paused for dramatic effect. I don't want you to worry too much, like, I don't get it. That would be like saying, like, imagine if somebody in regular calculus came to you and say, today they put a little prime on there and I don't get it. You're like, don't even worry about that at all. That is the least of your worries. You're going to now do this 1,000 times. I might not be exaggerating. We're going to do this 1,000 times. And we'll get to know exactly what this thing means. Yeah? Well, okay, what if f is negative? If the f is negative, when we multiply the y by the x, we're going to get negative values, which seems to throw the area thing under the bus here. So sometimes, if the function is negative, the integral doesn't give the area, it gives the negative of the area. It's still an area, but there's a negative sign outside to tell you this was underneath the x-axis. For you physics people, this really does matter. Force times displacement can be positive or negative. You can be adding or subtracting energy in all that. So there is applications to this negative thing. So we're not ignoring the negative thing. The negative thing is going to matter. But we want to separate sections that are positive into separate parts that are negative. So, but if we just want to talk about area, if you just want to stick to area for a minute, if things are negative, we just mean negative area. I got to rephrase that. I don't mean negative area. There's no such thing as negative area. But if I came out and did an integral, and I said, oh, the integral is -7, you'd go, oh, the area was 7. It's the negative of the area. Yeah? And so that's not all that big a jump to go to negatives. But there is something to understand here. If we don't break this into pieces, and we don't spend a ton of time breaking it into pieces, to be honest, because area is sort of the least of our worries in all this, then when we do an integral over a certain section, what we're getting is the net area. This area minus that area, which matters. Again, sometimes you want to know what's the total result of all this. And so you want to know, take the positive areas, take away the negative areas, take the stuff that was going this way, subtract the stuff that was going that way, and that's okay. That's a perfectly legitimate answer. But if you just wanted the area, you'd have to break this up and take these areas, then take the negative of these areas, and add these areas. So you'd have to do some thinking here. And I'll do one like that before we get too far. But please don't worry about all those details. Those details will come out in the wash. Those aren't going to cause us big problems. So here's the big statement. If you really want the area, find the area above the x-axis, subtract the area below the x-axis. That's what the integral is really saying. Is it's taking area above, subtract area below, and sometimes we just call that net area. You say the positives and the negatives sort of canceled out. So this wasn't the complete area, it was the net area. If you want the actual areas, you're going to have to find those zeros and do them separately. You'll see one of those coming up. Okay. This should be titled, this next one, go, blah, 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 blah. Show me how to actually do some. Yeah, that's what this starts off at. And it says, okay, let's slow things down a little bit. Let's go after a constant function. Let's rewind all the way back. This actually could be lesson 1 of the whole chapter and go, let's just slow it down and try and find some areas under some constant functions. Integrals of constant functions are very simple to evaluate. They can be calculated by multiplying the constant times the length of the interval. That is, if you've got some function that's at the same value all the way along, and you want to find the area underneath it, you just multiply its width by its height. And that will find the integral. See, the only thing we're doing differently here than what we could do in grade 9 is we're calling it the integral. And that will be true if it's underneath as well. What will the area be underneath? Find the integral. You'll get a negative value, and your area is the negative of that. Or if you want, when you look at this negative answer and you see like -10, your answer is 10 for the area. So you have to watch out for negative parts. It might be as simple as just taking the absolute value. Sometimes. Just go, well, I just want the positive part of that to actually talk about area. Some mathematicians don't bother with that, actually. They just go ahead and say negative area because they know exactly what they're talking about. You know, somebody will be like, you can't have negative area. Other people are like, I know it's not negative area. When I say -7, I know what's underneath, you know, area -7. I get it, you know. So here's theorem number 2. The integral of a constant. If your function is just constant and you want to find the area under the curve, you just multiply your constant times your width. And there's the width right there. That b minus a coming up again is just the width of the interval. Well, okay, that's not that exciting. Yeah, it's not a very good introduction to integrals really at all, because I probably could have taught you that in grade 8. You could have said, we're going to call the area under curve, we're going to use this little symbol, yeah? And to find it, you'll just multiply the height times the width. You're like, okay, I don't know what this symbol means, but I get what you're saying. So this is not a very exciting example. We'll do some more exciting in a second. Oh, all the way to examples. Okay, here we go. Let's actually do something. I've got this on a separate page, I believe. Do I? Is this what it says? Is this what the PowerPoint says? These examples? Okay, so you want a separate page. This is now doing some math. That was a long, drawn-out explanation. Lots of little details. And this is what we're trying to accomplish. I'll start using the symbols all the way through this lesson, and by the end of the examples, hopefully, that little integral symbol will be second nature. The interval -3 to 4 is partitioned into n subintervals. So they told us they want to go from -3 over to 4. Here's my little picture of what's going on here. They want to go from -3 over to 4. Whatever this curve is, and I don't know what it is, that's where I want to find the area of. Create an expression for the subinterval length delta x. So if I want to find delta x, which is the width of each of these subintervals, and again, I'm going to say, well, let's make them all the same size. After all that, yada, 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 that you can make them whatever size you want. Why would you make your life that difficult? Let's make them all the same size. And here's the fancy formula. To find delta x, find the width of the interval by going b minus a, and then divide by how many intervals you want. So here the delta x is b minus a, is, let's see, 4 is the upper interval. And then I totally wrote that wrong. Subtract -3, which is the lower limit. And so I get 7 over n. What does that mean? It means we're now ready to figure out how wide you should make the intervals. For instance, we took 4 minus -3 and said this thing is 7 wide. If you want 7 intervals, your delta x should be 7 divided by 7, which is 1. Makes perfect sense, right? If you want 7 intervals, they should be 1 wide. Let's say you want 100 intervals. then you take your 7 and you divide by 100. If you're really with me, you're like, isn't this the exact same thing that you were doing before? Just take the width and divide by how many intervals. Yeah, it is. B. If mk represents the midpoint of the kth interval, okay, so somebody decided that they were going to they made intervals here, and then here's the rectangle, and they were using the midpoint, apparently, of the interval. They're using MRAM. So mk is the midpoint of any particular interval. Expressed the limit as n approaches infinity, k equals 1 to n, 2mk squared plus 5mk minus 8 delta x as an integral. What? What are you talking about here? Let me just write down integral for a second, okay? Integral from a to b of f at x dx. That's what's going to be every single time. Lower limit of summation, upper limit of summation is like where are you starting this sum from, where are you ending this sum, the function you're talking about, and then a dx. Okay? So after all that blah, 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 what's the lower limit of summation? Where does this area start? That is, where do you want to start doing the area from? -3. So that's all they're talking about when they write this elongated S, is they're saying, go start from -3. Then, B is, what do you go up to? What's the highest you're going to go up to? And what's the highest we're going to go up to in this one? 4. Now the next question is, what equation were they using? See, all this other stuff is just the details. The limit as n approaches infinity up front is just saying, let's use a lot of rectangles. Okay? The k equals 1 to n is just saying, add up all the rectangles. See, fancy symbols, but they really don't mean much in all this. There's the important part there. Yes, delta x's. Of course, yeah. Multiply by the delta x's. There's the important part. There's the y value right there. They're saying whatever x value you have, go 2 times that squared, plus 5 times that x value, subtract 8. So the function here is 2x squared plus 5x minus 8. Questions on how I came up with all that? It's trying to transfer from Riemann sums to integrals. Upper and lower, and there's the function there. Forget about the n goes to infinity. Yes, we know we want lots of rectangles. Forget about adding them all up. Yes, I know, I got to add them all up. It's all in one notation here. Let's see, on a scale of 1 to 10 with integrals, when I first taught it, hopefully you're like a 2 or a 3. You're like, okay, so this just puts it all into 1. Now you're like a 3 or 4 going, okay, that's how I transfer over to this. And we're going to be using this a lot. What questions there? Remember, I just saw a couple eyes go really wide like that. Remember, I said, this is just intro. So this is like maybe like level 3 or 4 out of 10 is about the most you could probably be in all this, because it's really only the second example of these.
So we set it up as an integral, but like now what?
Oh, yeah, now what? Now 2 months. Yeah? It reminds you of derivative, right? So derivative. The first time I showed you a derivative, I did it on x. And here was the algebra. I've done it so many times. I went up to the board and I said, oh, we're finding the derivative of x. Let's see. Limit as h approaches 0 of f at x plus h over h. Oh, sorry, f at x plus h minus f at x over h. Let's see, x plus h minus x over h. The h's cancel. X over x, those will cancel 1. Limit as h equals 0, 1. Oh, the answer is 1. Yeah? That's the now what. It's like, now what? Well, now I got to show you a bunch of stuff about how to calculate integrals. You've pierced the problem. That's fine. You say, okay, you've made the notation prettier. You just spent 4 lessons making the notation prettier. Well, I argue there's a little more to it than all that. But you're right. Crazy notation, nice simple notation. And he says, yeah, but you still can't figure this out. You're going to go back and draw the rectangles? No. Great stuff coming. All right? So let's just assume that I've got some weapons coming to handle this stuff. All right? Let's presume that's what's about to happen. This is easy. I'm telling you, it's easy. Okay, let's switch back. Let's just say this appeared in your calculus friend's homework, and they're like, oh, we got to do y prime or something like that. I don't know what to do. Wouldn't you look at that and go, you'll be all right, sweetheart. It'll be fine. I'm stealing from Mrs. Todd there. Didn't she call you sweetheart when she's like, yeah, 4x plus 5. It's going to be fine. I'll show you. It's going to be fine. Yeah, it's going to be great. This is what he wants to know. How do I actually calculate intervals? I'm going to do constant functions and lines for now. We'll get to the other ones, okay? We're on our way. It says find the integral from -9 to 2 of 8 dx. What you really want here is a picture. What are you talking about here? Yeah? So here's my picture of what's going on here. I don't want that. Listen, I know the x-axis is in the way here. Or the y-axis, I'm not going to draw it on there because it just gets in the way of everything and confuses me a little bit. It says from -9 to 2, that's the first thing you got to understand about the integral, is these two numbers give you the lower and the upper. So I got the lower and the upper. Find the area under 8. What does the function 8 look like? Yeah? Hopefully we tripped on that thing enough to go, oh, it's the constant function of 8. So, here it is in red. 8. Now our job, I put dotted lines down there. Textbooks always put dotted lines down there to go, these are just imaginary lines going, this is the edge of the rectangle. There's not really lines there per se, but you could draw lines and it's not really a big problem. So my question is, what is the area under the curve? 8 from -9 to 2. It is that easy. If you got a brain that if the number's flashing in your head, if you're like, I know exactly what to do here, it is that easy. No trick coming. What's the width of this? Go ahead. Width of the rectangle is 11. And then what's the height of the rectangle? I didn't put it on there on purpose. I'm trying to force you to think just a little bit. But what is the height of the rectangle every single time? 8. This is 8. Area 88. Emmett's unimpressed. You're like, well, yeah, that's fine. You just grabbed a nice easy one. You didn't say how to deal with this one. Yeah, maybe I'll put that one up I'll put it up here for a while. Okay. Integral. What was the previous one? I forget already. Oh, there it is. It's there. -3 to 4. This is the one. We're going to celebrate when we get to the point where apparently that's going to be easy. And once we get to x squared, hey, any other degree will be fine. So we'll get back to that. For now, we'll just work on linear ones again. Okay, this needs a good picture. 2x minus 1, much more complicated than 8. We have to be careful how we draw this thing. So, I don't know if I was talking to you or talking to me. Mr. Todd, be careful how you draw this one. Integral from 0.5 to 4. That's the integral we're after this time. I've made no effort to draw this to scale because I don't need to. I just need to know 0.5 to 4. There's level 1 understanding of integrals. This upper and lower just tells me where to go along the x-axis. Then the line 2x minus 1. I already gave it away. My question was supposed to be, what does the graph of 2x minus 1 look like? Boy, that's supposed to be easy to us by now. We're supposed to be like, that's a line. And it's going up. So I'm going to get the initial point on here and the final point on there. And that will be plenty to be able to find this area. There's the line. I need the coordinates of those points, though, to be able to do this. So I got to sub in 2.5 into the function. Or sorry, 0.5 into the function. 2 times 0.5 is 1. Minus 1 is 0. Oh, whoops. Yeah? And when that happens, I always draw them non-zero, and then sometimes I get surprised and go, oh no, it's 0. So let me just get rid of that for a second and draw a better picture of this line. This line starts at 0, and then it's y value when x equals 4. Oh, so yeah, 2 times 4 is 8, minus 1 is 7. So up here, this is 4 comma 7. And so my straight line in red, there's my line. And I'll draw the little dotted line at the end, just to finish off the shape. What, what shape is this? It's a triangle, yeah? So, another nice, easy integral. We want base times height over 2. What's the base? I can see the base is 3.5. Are you okay with 3.5? I don't got to do b minus a anymore. 3.5. The height here, ooh, that's going to take just a few cells of brain power there. We're going to have to turn on a couple of things here. Wake up just a little bit. What's the height of this triangle? 7. It's the y value given there. So height 7. And I got to divide that by 2. So 21, 24, 12.25. I think 12.25. I've been off for months here. I don't trust my brain. 12.25. Okay. Again, you're under pressure. Like, well, yeah, straight lines, goody. Well, okay, straight lines aren't completely easy. That was nice because it started at 0. The next one doesn't do that, I believe, if my memory serves right. -1 to 5. Oh. Oh. There. They want, was I using blue all the way along here just to be consistent? They want -1 up to 5. Y equals x plus 3. What does the curve x plus 3 look like? A straight line, yeah. And so I just need the 2 endpoints to get a picture of what's going on here. So I sub -1 in, I get 2. That's -1 comma 2. And it goes up to this one up here, 5 comma 8. Okay, this one's a little bit more difficult. I'm going to draw my dotted lines down here. That thing is not a rectangle. It's not a triangle. But did you have any suggestions on how to find the area of this thing? Yeah, you could go find the trapezoid formula. Well, we're gonna have to go after trapezoids sometime soon. So we'll just leave it up there. You get simple shapes like this. You could probably just do a little work like this and go, okay, so I got to do base times height of that rectangle, and then I got to do base times height over 2 for the. I just put little 1s and 2s there because maybe they're not the same bases and heights for each one. The base of the rectangle 6. Its height is 2. The base of the rectangle is 6. Its height is 6. And I get 30. You take a look at that for a second to see if you get the same as I do. Questions on where I got the numbers from? Any questions on where I got the base of the rectangle? Height of the rectangle? Base of the triangle? Height of the triangle? That took a little bit of thought. 8 minus 2, to get that little height there. I can see your brain drifting a little bit. So take out your calculator, please. And let's play with your calculator for just a minute. I've got to find mine again. There it is. Okay, so calculator on top there. Okay, so I'm just going to put this right there. Okay, and menu 1 to get to this mode here. Now, you were in linear mode before, right? I want you to switch over to math mode. How do you switch over to math mode? You got to go to setup. So you go shift menu, and it says linear at the top, which is right for using the programs and doing Riemann sums. For everything else I can think of, math mode is way better. So let's switch back over to math mode. Math mode, and then exit that menu. So I hit the exit button, shoot back to here. And along the bottom, you should see different. You might not have noticed it changed. Jump, delete, a weird little triangle, and then an MAT, that's matrices, which we're not doing any of those. Then math. I want you to hit the math button. And look at the things it does. It does matrices. I can't read what that next one says. And then absolute value. Ooh, absolute value is in there. So when you run into absolute value, there it is. And then it does d by dx. D2 by dx squared, which is the second derivative. Press the over arrow. So good. Press F6. Integral. Press F1 and look what you get. It's so good. It says, okay, yeah, what's your integrand? I'm going to use the fancy words. What's your integrand? And my integrand here was x plus 3, so I enter x plus 3. Lower limit, -1. Upper limit, 5. I find it easier to enter the integrand, then I arrow to the right, and then I can put those in. And great for checking answers, it says 30. That's not how we're about to do them. I can push this thing in there and I get the answer. We're going to find out how to do these things because the calculator won't always be able to help us or won't always be available. Okay? I just throw that out to you so when you're doing these things, you do some area calculation, you want to double check your answer, you'll be able to do that. Oh, okay, one more. Negative 2x from -4 to 3. Or from -3 to 4, sorry. Negative 2x is a line, so I just need the two endpoints so I can see what's going on here. If I put in x equals -3, I get a 6. So this is -3 comma 6. If I put in x equals 4, I get -8. Uh-oh. Connect those two up there. It meets at some y value. I'm not trying to be accurate, so I don't know exactly where that y value is. But without that accuracy, I'm out of luck here because I don't really know where to find that. This is where the positive negative thing comes in. Like, I'm going to do this area, and I'm going to do that area separately. I really need to know this value here. And my drawing doesn't do a very good job of it, but I'm going to fix it. When does y equal 0? In this thing, when x equals 0. So I'm just going to grab this. I'll just put it right there. That's a fix afterwards. I'm like, it happens to go right through that. It doesn't have to go through the axes, or the origin, but this one happened to. When x equals 0, y equals 0. So I've actually got two rectangles here. Two rectangles. Two triangles here. Getting a little punchy after teaching all morning here. So I got two triangles to do here. Important thing about the integral coming up though. If your brain has drifted off, you're like, so you just spent half an hour teaching triangles and rectangles? Yeah. Actually, I wasn't teaching triangles and rectangles. I was teaching integrals. So you get to feel what's an integral. What is an integral? That's what this slide is. But an important thing about what is an integral coming up here. Simon. Oh, because I said, when will the y value be 0? When will this be 0? So I need to know when does -2x equal to 0? Divide by -2 when x equals 0. Good question, yeah. This one was set up to be nice, because we're really not trying to beat this idea to death. But there's an idea coming here. So let's go after each of these things. So maybe we need this triangle, which is base times height over 2. So again, I'm going to go B1, H1, just to be technically correct, because there's two different triangles here. I should give them each a different name. And then I'm going to not write what goes in between, because that's really the point of this question. I'm going to find both these triangles, and then we're going to talk about what to do with the two areas. Okay? Because there's a very important idea that you may disagree with, but it's the way this is set up. You need to understand this is the way it's set up. Okay, so the first triangle is base 3, height 6, and the second one is base 4, height, I can't read my own writing there. Is that an 8 down there? Negative 8. So the height of that triangle is negative 8. I know what you're thinking. Or what you should be thinking. If it's an area, shouldn't we just use 8? I don't disagree. I don't disagree. Maybe that should be positive 8. I'm going to keep it like this and explain the whole thing, okay, by the time we're done. So what I end up with here is, that's 9, and then this would end up being subtract 8, which is the number 1. 32, that's 16. I divided by 2 twice for some reason. Negative 32 divided by 2 is 16. This would be negative 7 would be the area. You're like, negative 7? Well, how do you get negative area? And first of all, why did you subtract the areas? Important note. That's what the integral does. The integral doesn't find area. It finds, excuse me, can you move up there, please? It finds net area. If you want the area, yes, the area is 9 and 16. The area is 25. Absolutely, the area is 25. The integral is negative 7. That's a little bit of a tricky idea there. This word really helps bail you out, though. Integral calculates net area. Positives subtract the negatives. And we really want it to be that way for applications. We want there to be a difference between positives and negatives here. Positives add to things, negatives subtract from things. Positive displacements, negative displacements. Positive energies, negative energies. That's really the way we're going to want that to be. Questions there? More time there? More. More. Evaluate this integral. Negative 2 to 2 of square root of 4 minus x squared. This is going to come back to haunt you, so we're coming right back at it again. I already taught this once today, what this equation is, but while I'm drawing the axes, see if you can reach into your brain and go, what does square root of 4 minus x squared, what is that thing? That is, what is y equals square root 4 minus x squared? And, I take this back. Remember earlier I said you saw it in grade 10 once and advanced functions once? That's not true. In chapter 1 of this course, way back in September, we beat on this a little bit, didn't we? We hammered away at circles. So this isn't so bad for you, is it? You know x squared plus y squared equals r squared. So I'm just going to move this around. That means y squared equals 4 minus x squared. Move the x squared over. X squared plus y squared equals 4. I gave that too much credit. You saw that. Remember, x equals cos t, y equals sine t, all that stuff. Okay, so here, this is a circle, radius 2. Better than that, here it comes. Here's me drawing a semicircle here. Oh, not bad for me. It's a little flat on the outsides. It's like the Earth, right? A little bit flat. Why did I only do this half of the circle? It didn't say plus or minus. It was only the positive side of this thing, yeah? So to find this integral, I'm just doing pi r squared. you know what? You really should be unsatisfied with what I'm doing here. You're like, so you're just drawing the pictures of the functions and finding their areas? That's really what this is going to be about? No. This part of the lesson is called getting to know integrals. Getting to know what they look like. Another lesson actually 2 or 3 more lessons before we can do algebraically. Yeah? Find this answer. If you want, the analogous lesson in calculus would have been, which I didn't do, which is let's spend the day drawing tangents on the, draw another tangent. Oh, here's a curve, draw a tangent. That's what we're doing here, getting to know integrals. Pi times, what is the radius of this thing? 2, so I get 4 pi. You could get a decimal there, but 4 pi is just so much easier to write. I don't have to write 12.56 all the time, The area under square root is 4 pi. And stuff like that boggles the mind. Oh, let's try it in our calculator, just to practice that out, okay? Let's see. Integral. See the integral button still on the screen there. Square root 4 minus x squared. Right arrow over, and that'll take me over to the lower limit if I do it a couple times. Negative 2. Right arrow over to the 2 equals 6.28. It's not 6.28. I got 12.56. Because I did a full circle. Half circle. That's why the calculator is so handy. Jam those things in there to make sure you did your integral right. All the way along here, you're going to have to show your steps of finding integrals. Welcome, gentlemen. But your integral calculator is there to double check to make sure you did the right things. Did I fool you? Did you think I made that mistake on purpose or not? What do you think? Do you think I forgot? You can't tell. That's good. I completely forgot it until I put it in the integral thing. I just said pi r squared. Were you going to let me away with it? Was anyone still with me enough to awake enough here? Oh, you were ready. He was ready. Like, I'm going to break this thing into by the end here. 2 pi. 6.2. Yeah. 6.283. I know, but 2 pi is so much more convenient to write it like that. Questions there? You're going to hear me change my phrasing. 2 people who haven't seen all these. Can you imagine? I haven't seen all these lessons all morning trying to jump in the middle of this. So you're going to hear me change the way I phrase things a little bit to try and help them out and bring them into the lesson. This says if a, b, and c are constants, prove algebraically that the integral from a to b of c dx is c times b minus a. What? Here, inside here, the integrand is a constant. And they didn't tell me what the number was, but they said it was a constant. Here comes my phrasing for our people who have just joined up here. It's saying we're finding an area. And this area we're trying to find goes from A to B. And they didn't tell me what A and B are, but they just said it goes from A to B. Then they said it's a constant function. And they didn't tell me what it was. But what does a constant function look like? If you go to draw a constant function, what kind of curve are we expecting when you get a constant function? Let me give you some examples. Y equals 7, y equals 20, y equals 50, y equals 8. What kind of function are you expecting when you get a constant function? Just a horizontal line. So there's this horizontal line that goes across like this at value C. I'm well on my way to proving that this area, or what this area is. I'm going to ignore what they said to prove. Yeah. Sometimes that can be distracting. Sometimes when they do a proof and they want you to prove something, it's good to look at what you're trying to prove. And other times it just distracts you from what you got to accomplish. So we'll just go ahead and do this. Area equals, well, what shape are we talking about here? Rectangle. What's its width? Oh, that's hard. Let's do its height. What's its height? C. And then what's the width? How far is it from A to B? B minus A. Okay, so, I'm done. Therefore, the integral from a to b of a constant will just be c times b minus a. Handy little theorem when you're just trying to find the areas of constant functions. We've got pictures now for linear functions, those last few. Still looming. Higher degrees. We'll get there. Any questions about that little proof? What time's your lunch? Did I just teach right through lunch here? Oh, 12:50. Well, the time's going to work out. Well, good and bad. I'm committed to teaching well. I'm well aware of the clock. I'm well aware of the dates. I'm well aware of the snow day. I'm well aware of me having to be away tomorrow. I'm aware of all those things. But what I teach, we're going to teach well. We're going to know the stuff I do well. And we're going to go hard until they say, that's it. You've got to go take 2 different classes now. That's what we're going to do. Okay? That's all we can do. Teaching it poorly will not help us. Questions here? Use the integration function on a calculator to evaluate the following. Oh, so that's what I was saying. I already introduced that, is you can get your calculator to find these integrals, even if you don't really know what an integral is. You can get your calculator out and find an integral. Here, I warmed up a couple of calculators here for you guys. I think they're very functional. So let me review what it takes to get an integral into a calculator. You must be in math mode. So I'm just going to double check that again. I go up to shift setup and my choices are math and linear mode. Sometimes I want to be in math mode, other times in linear. Here I was in math, want to be in math mode, so I hit F1 to get it into math mode. Then I just go to the menus at the bottom. I got jump, delete, matrices, and math. I go to math and I go F6 to get more math functions, and there it is, the integral, and I get to just fill them in. The integrand, he said using the fancy words, is the function inside here, x sine x. And as I'm typing this in, maybe you're thinking, no, wait a minute. You're saying this integral function does exactly what the Riemann sum thing does that we were doing yesterday, and that we were doing with the other part of the program of the calculator. This does the exact same thing, just with an infinite number of rectangles. Yes, that's exactly what the integral does. When you do the Riemann sum, you're like, I've got a certain number of intervals. When you do integral, you're going, no, take it out to infinity. Get the answer for me. How's it doing it? I don't know yet. We don't even know how it's doing it. What was it? X sine x from -1. I just typed that in wrong. -1 up to 2. Do you get what I get? 2.04. $275. 9779. Yeah? And great for checking answers. Yeah? All the way through. No matter how complicated the integrals get, more complicated than hard to draw on the screen, or harder than we can even do right now, or harder than this needs. Oh boy. I recognize this baby. This one is tough. Yeah? When we get to that one in the homework, I'll be like, hold on, let me just teach for an hour, and then we can talk about this one. Okay? Big trouble, this one. Well, it's not big trouble for the calculator. The calculator just goes, okay, integral 4 over 1 plus x squared from 0 to 1 equals we recognize this old friend? Integral of 4 over 1 plus x squared is pi? See, pi pops its head out in other places. I think pi is just about circles. It's got a way of just maneuvering its way into things. More to the story. Don't go away. It's okay. We got weeks to go, right? Yeah? There's more to the story. Something going on there. Yeah? We'll get back to it. This is just about the calculator. Forget about the pi. Okay, that's fine. Pi popped up. Big deal. Okay, integral. E. Oh, good. I'm sure you missed the exponential function. People shaking their head. No, I didn't miss the exponential function at all. It's back. Okay, so where's E on this thing? Well, I can't even read my calculator on the screen here. Is it over top of ln? Oh, yeah. E to the negative, okay, our calculator doesn't do t, so we do x squared, that's fine. That's just a dummy variable anyway. We talked about that. The fact that we're using x's instead of t's isn't going to change the answer. Just because you change the name of the axis, it's not going to change the value of the area from 0 to 5. Do you get 0.866? 0.88, was it 8? I just said 866. No, 886. 226, 9255. Right? And the reason I'm doing so many decimal places is to make sure we know exactly how to type those in and check our answers. Questions there? How much time do I got? 25 minutes before lunch. Do you have a headache? I do. Yeah? Big one. Yeah? This is how we power through, right? Is this the last one on this lesson? Is it? Okay, good. The following integrals involve functions with discontinuities. As promised, I said we'll deal with functions that have discontinuities. We can deal with some discontinuities. Some situations won't hold us up from finding areas. And I'll show you how we got to deal with each of these types here. I don't know if I'll fit them all in on this one. I might need multiple pages to be able to draw everything you need here. The first one's an absolute value, which again, you're like, absolute value. I remember there's big problems with absolute value. I really haven't thought about it since November, but there's big problems with absolute value. So let me just do a quick review on absolute value. Let f at x equal absolute value of x over x. I'm going to give that integrand a name, f at x, so I can just deal with it and play with it, so I can understand what's happening here if I'm going to find this integral that apparently has some kind of discontinuity in it. That's step one. What kind of discontinuity are we talking about so that I can go ahead and find the areas needed? So, let's talk about absolute value. What is the important x value in absolute value? See, the rule changes for absolute value. On one side, it has one rule. On the other side, it has a different rule. What's the important number? What number splits absolute value in half? 0. Yeah, 0 is the important number here. So actually, when you actually want to do anything with absolute value, besides just subbing numbers in, you should really go to the piecewise version of this. Here's the piecewise version of this function. And that whole question about 0 was just so that I could go, okay, I need one function for x greater than or equal to 0, and then another function for x less than 0. So let's rewind to absolute value for a second. What's the, see, the advanced functions people just did this. What's the absolute value of 5? 5. What's the absolute value of 10? 10. What's the absolute value of 20? 20. Absolute value has a simple rule when the x values are positive. And the simple rule is, don't do anything. You don't have to do anything. The answer is whatever the number is. That is, if the x values are greater than 0, then absolute value of x is just the x value. So you get x over x here. Is this starting to ring a bell just a little bit on how to handle these? Now, full explanation again, as if you've never seen it before, because it's been a couple of months, right? What's the rule on the other side? When you want to do the absolute value of negative 3, what answer do you get? Positive 3. Negative 9 becomes positive 9. Negative 20 becomes positive. You've changed the sign. You've got to take whatever x value you have and change its sign. What's our way of handling that? We go, oh, take your x and change its sign by multiplying by negative. So I get this as my function when the x values are less than 0. So if you've got a negative x value, change its sign. That's all this is saying is, if you've got a negative x value, change its sign. So I get as my function here, this function is 1 for x greater than or equal to 0, and it's negative 1 for x less than 0. Now I'm ready to draw a picture of it, and then find its integral. And its integral is just the area under the curve. That's all we're talking about. It's fancy symbols for area under the curve. Picture. What do I got? Negative 1 to 2. Mr. Todd, do I have to draw a picture every time I want to find an integral? For now, yes. I got 2 big theorems to hand you. 2 big powerful theorems. I was hoping to get to them today, but if I don't get them to them today, we'll have to work out what we're going to do next. So this function, when x is greater than or equal to 0, has value 1. When x is less than or equal to 0 or less than 0 that has value negative 1. Let me just put a couple dots in there, a couple dotted lines. Oh, this is 1. This is negative 1. So actually, the fact that this thing had a discontinuity doesn't stop me from taking its integral. It does force me to think a little bit about what the integral would be. So I've got one rectangle, base 1, height 1, and then I got another integral, base 2, height 2, and this positive negative thing is going to come up again, and I want to talk about that and make sure that I hammer away on that. The first rectangle is 2 times 1, and the other rectangle is 1 times negative 1. And so I get 2 minus 1. I only get 1 as the area, which boggles your mind. So I'm hoping somebody has the phrase that bails us out of trouble to make us understand what integral is all about here, is that this had area 2, this had area 1, and you're saying the integral is only 1. What happened here that the integral, how can areas come out to less than what the areas were before? What is the integral? Net area. It takes positives and subtracts negatives from it, and you end up with only the net area out of that. So whenever you're doing one like this and things get a little confusing, go ahead and write net area after it to remind yourself, this isn't the area total. If you want to find the area total, I should have done something different. If I wanted area, I should have gone 2 plus 1 for the area. I should have subtracted that negative area. Less complicated than it sounds, really. You know, the net area really explains what's going on. Questions there? I'm trying to throw out little tidbits out of those of you who have missed most of this stuff this morning, but this whole video, I'm doing the whole thing, so it'll all be up there. So if you jump in and you're like, whoa, what is going on here? Yeah, it's good for you. I don't have room for this here, so just give me a second here to duplicate that page. There it is. Okay, and then duplicate that page again. I'll go to this page and I will give it the old spritzer. Get up there. I'll just lock that down. Grab all this and drop that in the trash. Still got the old one? Yeah, still got the old one. There's the new one. And there's the new one. Okay, so grab that and lock it down and clear all this stuff and drop that in the trash. And little Iron Man go in there, just clear all that stuff out. And now I'm going to do B. Yeah, after all that. Says integral from 0 to 3 of x squared minus 4 over x minus 2. Let's talk about what that function is. Again, I'm going to give its name. F at x equals x squared minus 4 over x minus 2. Okay, reach back into the recesses of your mind. I didn't put any holes on tomorrow's test, by the way. But why is this one, why is the discontinuity here a hole? Because they cancel. Oh, yeah, you do sort of remember that. Reaching back and going, okay, when this canceled, and there's an important thing here that maybe we only did a good job of explaining before, is that the function x squared minus 4 over x minus 2 is the function x plus 2. It just has a hole at x equals 2. So if I go to draw this thing, hey, I don't want red for my x's. There, that's better. Space for the graph, and then a little space to find my area. The function y equals x plus 2. I'm going from 0 to 3. Oh, well, that's not so bad. I'm drawing y equals x plus 2 from 0 to 3. So it's got to start at x value 0. It's going to have a point, and then it's going to go upwards, and it's going to end up somewhere up there, like that. Coordinates of these points, this is 0, 2. And then this one is 3, 5. There, I've graphed that line from x equals 0 out to x equals 3. That is not the correct graph of this. That is the correct graph of x plus 2 from 0 to 3. It needs a hole. So I need a little white pen here, maybe a big number here. And at x equals 2, right about there, oops, right about there, this thing has a hole. So let me just, and I'll make the hole giant, even though it's not supposed to be really giant, but I'll make it giant so you can really see it here. There's a hole there in the graph. And to show that the hole is there, we draw a little circle around it, even though there's no circle on the graph. That's just us drawing like a little magnifying glass to say, hey, look here, there's a hole in this graph. The good news is that doesn't stop me from finding the area under it. A hole is not really a problem in finding the area. That is, what I'm going to do is I'm just going to find the area of that piece and add it to the area of this piece, which if you look at it, it's the same as finding the area of the whole piece. It's not really a problem at all. Holes don't really affect the area. It's this infinitesimal little stripe missing in the area, which doesn't contribute to the overall area. It's just one little tiny piece in there. All I'm saying is that this whole area is equal to the sum of these two areas. So I don't have to go through all that to find this area. What do we see here? Well, hopefully you see a trapezoid, but again, we decided to put trapezoids up there. We're going to go rectangle and triangle here. Base times height for the rectangle, and then triangle. So let's see, the rectangle is 3 by 2, and the triangle is 3 by 3 divided by 2. I'm going to check that in a second. I did that really fast, but I think I get 10.5. How did I get the base of the rectangle? I was going from 0 to 3, so the base of the rectangle was 3. The height of that rectangular part at the bottom was just 2 because I was going up to 0, 2. And then the base of the triangle was 3, and then the height was that 5 minus 2, 4.5, so I get 10.5. And of course, you've always got your calculator ready to rock and roll. But your calculator can handle these, even if we can't. Integral from, let's see, function, fraction, x squared minus 4 over x minus 2 from 0 to 3. 10.5, yes, all right. Well, what questions do you have? We have 14 minutes, 14 minutes to lunch still? 12:50 is lunch? What questions do you have? This is supposed to be boring you to death at this point. You're like, okay, I got it. Integrals in that area. Can we get on with things? Yeah, absolutely. We need that absolutely entrenched. Like derivatives. We needed it entrenched that the derivative was the tangent slope before we could move on. One last example. I've tried to do these, so I'm reviewing stuff from the other quadmester now. Yeah, absolute value, a little bit of hole, and then this thing, which you might have forgotten about completely, so we better talk about that one. Move my calculator up. Oh, calculator. Will. There you go. Textbooks on your desk? Textbooks? No textbook yet? Textbook? No? Okay. Last one before lunch. You got one? You got one. Oh, I'm better than I thought. Last one. Int function. Does anybody remember? Hey, well, look what this does on the... I don't know why that's doing that. Okay, yeah, don't care. Stop that. Well, what does the int function look like? Yeah, it's the staircase, yeah? And it's like the round down function, you know? Zeros, ones, twos. Okay, so this won't be hard to find the area under at all, really. Yeah. If they use nice x values, which I think they did here. So very quickly then, this example. thick red line to show the different sections of this graph. 0 for a while, then 1 for a while, then 2 for a while, 3 for a while, 4 for a while, and that's it. So the area here I got a 0 rectangle, then a 1 times 1 rectangle, and then a 1 times 2 rectangle, and then a 1 times 3 rectangle, and then a 1 times 4 rectangle. How do I do in brackets? One too many? Okay. And so I've got 0 and 1 and 2 and 3 and 4 areas 10. Okay. So that's more of a review of the in function than a review of integrals per se. We're just finding the area under each one of those. Here's the rectangles. No function more ready to do Riemann sums with rectangles than the in function. It's like, here's the rectangles. It's screaming at you. Here's the rectangles you should use. And this isn't an estimation at any level. The Riemann sum would look exactly like this. Yeah, so it's kind of a fun function to do these things on. Questions?